And then I feel like one.
Hey guys, as you come in, please fill out the attendance form and also if you want to follow along with our workshop today, then open up the workshop notebook link. And if you're online and you need the attendance form, give me a second.
As a joke. I was watching. I was like, here we go. And no, it's just something else. I think good. I had good. I have like okay, maybe.
The last.
So that's cool. Sorry. That sounds like I'm not like especially like a quantity as it says. That's actually tough, but then I'm not. I have to think of it. Is there actually like photo?
I'll just finish my homework and give you the pen and leave.
Well, the attendance. Would you? How'd you like this?
Everyone who's coming in, please fill out the attendance form. It's how we get money for snacks and pizza. So yeah, please fill out the attendance form. And yeah. We don't have pizza this week. We have snacks this week, but hopefully we'll have more pizza coming in future weeks.
You like astrophysics?
Can everyone online hear and see the Jupyter notebook or the collab notebook? Was it
There was. Like shifting. Like astrophysics.
You can do it on your end, okay, great.
Now I do. Yeah.
Okay. And it's recording.
So the whole land. One of the system. Yeah, I can.
Yeah.
Oh, that is such a good idea.
Last call, does anyone still need the attendance form? Or does anyone still need the QR codes for the workshop notebook?
Workshop notebook.
Yeah, the one at the bottom there, in the workshop.
The one at the bottom.
Yeah. Well, let's get started at like 6:10.
Yeah.
So for those who weren't aware, today we'll be doing a workshop on quantum computing, just like an introduction to quantum computing for people who are new or need to like refresh on their background. And then we'll be doing this interactively with Qiskit. So it won't just be, a ton of math. It'll also be actually how do you apply this stuff in a language or a library like Qiskit so that you can code your own quantum circuits. And yeah, if you're interested in joining the project, definitely, pay attention. This is all stuff that'll be really useful to know if you're working on the code base. Last call for QR codes before we get started. Anyone still need them? Okay. If not, then yeah, I guess we can go ahead and get started. Let me make them both me. Hopefully that works. Yeah, great. Okay, so welcome guys to the Intro to Quantum Computing and Qiskit workshop. This is our first workshop of the semester. This is the second workshop that we've held as QCA, so it's pretty exciting, and we'll definitely have more of these. So if you like what you see, stick around. And yeah, we'll have another one next week, which will be focused on quantum error correction. So yeah, this is meant as like part one to that. So if you have any questions on any of this, then definitely stop me, just interrupting, and I can answer your questions. And if you have like issues like errors on your computer, just maybe come up to the front and then ask Fiend, maybe can take a look at it quickly for you. But yeah. Otherwise, yeah, so this is meant to just be a general introduction to quantum computing. It's not going to teach you the entire field. It's not a replacement for Mike and Ike or John Whitehouse's like YouTube series, which I definitely recommend checking out if you haven't, but it's just supposed to give you like pretty much everything that you need in order to get started on the project or work on your own stuff in quantum computing. So when you're doing quantum computing, you're gonna probably use a library like Qiskit. So Qiskit is a library made by IBM Quantum's team, and it's really popular, used by a lot of researchers, including us. This is what our code base is built off of. So the first thing that you'll want to do whenever you're doing, anything quantum computing, zoom in a bit. Can everyone see the text okay? People in the back? Okay, so the first thing you'll want to do is import, or well, first actually install Qiskit. So there's a couple libraries that are involved. So there's Qiskit, which is like the main, like how you make quantum circuits. There's Qiskit Air and Qiskit IBM Runtime, which are for simulating quantum circuits. So, actually running them on your computer, not on a real quantum computer, but like just on your computer locally in a simulation and then getting results back. And then there's also libraries like PyLatex, and PyLatex and Matplotlib, which are used for visualization, things like that. So if you just run the cell, if you're new to Jupyter, this should work, hopefully. It might take a second or two, but as soon as it finishes, you can ignore these other lines that are just there for cleanup. So yeah, once you've like installed Qiskit, this would be like, you can install it on your computer, you can use it in a notebook like this, wherever you want. Once you have that, then you're ready to do stuff. So when you're doing anything with Qiskit, you're always going to import a couple basic things for the most part. You're going to import a quantum circuit, and then you're also probably going to import registers. So we'll talk about this a bit more as we go, but for now, just import them. Trust me that you'll need them, and then we'll explain them now. So yeah, again, you can like Control Enter, Shift Enter, or just hit the Run button to run the cell. So once you've imported these, you may be asking, what are these actually doing? And this is where we actually need to talk about how quantum computing works. So when you're doing classical computing, you'll have things called bits, right? You might have heard of like bits, binary. On your classical computer, these are represented using voltages, like zeros and ones. And so those are just like high or low voltages. Whereas in quantum computing, we have qubits. And these qubits can also be like 0 and 1, but they can also be arbitrary linear superpositions. So this just means like a 0 plus a 1, with some probability of being a 0 and some probability of being a 1. And so when you have qubits, you put them in what's called a quantum register. This is just a set of qubits. You can have multiple quantum registers when you're doing a quantum computation, and you can have multiple qubits in a quantum register. It's just a way of organizing your qubits. And then when you have classical bits, because we still need to do, some classical computations in quantum computing, you have a classical register. So you can say, okay, I want 2 classical bits, sometimes called CL bits or C bits, and you can say, I want 2 qubits. Okay, and then once you have that, then you can make registers. So these just store that many qubits or CL bits. Some people might be like, why are you using registers? You can just directly input the number to quantum circuit. I recommend using registers a lot of the time, because if you have a register, you can reuse it. You can say, okay, I want this register to be part of 2 quantum circuits that are separate. I want to maybe like combine them later. Whereas if you just have different qubits in every single quantum circuit, you can't reuse your qubits. It would be like having a quantum computer, but every time you ran a new algorithm, you had to get new qubits instead of reusing the ones you already had. So having registers is good practice usually. So yeah, you make your quantum registers, and then you're good to go. You can start putting them in a quantum circuit. So you can call the Qiskit quantum circuit method, which will create a quantum circuit with their qubits and CL bits, or C bits, whatever you want to call them. So that was a lot of code to, get stuff set up, get you like the foundation built. But you might be asking, like, what is actually happening? We made these like qubit things, and we made this quantum circuit thing. What's actually happening? And so you can draw it. So Qiskit quantum circuit has a draw method. So it's just qc.draw, and then you can say how you want to draw it. So for example, you can draw it with text, just like that, or you can draw it using the matplotlib drawer, which is why we install those other imports. So here you can see a quantum circuit. So what's happening here is you have 2 qubits. These are these wires, as they're called, labeled Q, and then you have 2 classical bits. These are the wires labeled C. So anytime you do a quantum computation, or even a classical computation as part of your quantum algorithm, they're going to be affecting these qubits. If you want to do a bigger quantum computation, you need to have bigger qubits. So like we requested 2 C bits and 2 qubits, but you might want like 1,000,000 or 100, whatever, and they'll all show up in the circuit. So yeah, you have these qubits, they're in your registers, they're in your quantum circuit, and now you can do stuff with them. right? So all quantum computation is about taking your qubits and applying special operations, which will put them in states that you want them to be in, which represent your computation. So when you can make a quantum circuit just like this, as we did before, and then you can apply operations. So don't worry about what these operations are just yet. This one's a Hadamard and this one's a C naught or CX, but we'll explain that more a little bit later. There's also barriers. But the point is you can take your quantum circuit and just like this, apply operations to them. So just like if you're doing a classical circuit, you might have like voltages coming into your circuit, your PCB, whatever, and then you say, okay, put it into an AND gate or a NOT gate or whatever. Just that same way, we do the same thing here with quantum gates. So yeah, you can run the cell and you'll see you have quantum operations on your circuit. So the way you want to read this basically is from left to right. This is like the passage of time. On the very left, you say, these are my qubits. I'm creating them. I'm like bringing them into this world. And then I'm applying these operations in time order. So first we say, take the qubit 0. So it'll just be like 0 indexing. Take qubit 0 and apply a Hadamard gate to it. That's what that square means. And so the Hadamard gate is just one example of a quantum operation that you can do. And this is called a single qubit operation because as you can see, that box only affects one qubit. It's only on one wire. Whereas the next operation is called a C naught. Again, we'll explain this later, but it's a 2-qubit operation because it operates between the qubit 0 and the qubit 1. So these are like examples of quantum operations that you can do, and there's a million more. There's like examples down here that we'll get to later, but yeah. This is just like the very basics, like this is how you make a quantum circuit, put operations, and visualize it. Very simple, or very little to do there. And I will say, if you've heard of something called a quantum annealer, this is what D-Wave makes, for example, they don't use the same model of quantum computation. So this is called the circuit-based model of quantum computation. Most of the algorithms that you'll hear about, like Grover's algorithm, Shor's algorithm, like variational quantum algorithms and all these different things, most of them are built off of the circuit model. There's just certain cases where it happens to be better to use different models, like quantum annealing. So we'll be focusing on the quantum circuit model for this, but if you're interested in these other models, definitely go ahead and look into them or like ask about them in the Discord and we can talk. Yeah, so there are, like classical operations like AND and XOR and NOT, but when you're doing quantum computing, we don't have all the same examples of gates. And one of the big reasons is something that's called reversibility or determinism in quantum mechanics. So what has to happen for any valid quantum transformation is it has to be reversible. So let's say I have a quantum operation that's like an AND gate, okay? Or let's say a classical operation, which is an AND gate. I take in 2 classical bits and I apply an AND operation, and the AND operation stores its output in one of the classical bits. In general, that's not reversible because what you did is you wrote over one of the existing classical bits that you use for your input with the output of your measurement. So now how do you know what the input of your measurement or the input of your circuit was? You don't because you wrote over it. And so you can't do that sort of thing when you're doing a quantum computer. You have to have reversible operations besides measurement. That's the one exception. So Discord. For those of you who are joining late, by the way, we're going through this workshop notebook and it'll be sent in the Discord in just a second. So yeah, that's just like a background what's happening with these quantum circuits. So what's actually going on, you might ask. So you want to, you'll want to make a quantum circuit, but you'll also want to understand what's it actually doing? What state am I preparing in? What operations am I doing and how are they affecting my qubits? So you can use something called a state vector. This is how we represent quantum states. So just like how classical bits can be represented by binary strings, like 0, 1, 0, 0, 1, 1, 0, that sort of thing, we have quantum state vectors. So these are the quantum mechanical descriptions of quantum registers and quantum circuits. So you're going to do this new import from qiskit.quantuminfo called state vector, and then you can apply the state vector method or class to your quantum circuit, QC. And by doing that, and also drawing it, of course, you get to see the state of your quantum computer at the end. So, at the beginning, we had these qubits, right? We had Q0 and Q1. This is basically saying what state did those qubits end up in. So don't worry about like how this happened just yet. Again, we're gonna talk more about like the specific gates and operations more later. But what's basically happened is we took qubits, which just like in this example started in the zero state, so like 0, 0. So qubit 0 was 0 and qubit 1 was 0. And we put them in this arbitrary superposition. So I told you like classical bits can be 0 or 1, right, at the end of a computation. But when you're doing a quantum computation, they can end up in this sort of arbitrary superposition. If you take in linear algebra, this is just like a linear combination of vectors. You know, you have like your x basis vectors and your y basis vectors, and you can add them like 0.5x plus 4.8y, that sort of thing. And that's the exact same thing that we do in quantum computation. We take zeros and ones and we do linear combinations of them to get arbitrary quantum states. And the thing that makes quantum computation really effective is being able to do these superpositions and things like entanglement, where you're basically able to do more stuff in a quantum computer than you are in a classical computer. So these are very unique features to quantum computing that don't exist with a classical bit. So yeah, this is a example of a quantum state vector. This is, as I say here, it's called the Dirac or Bra-Ket notation. These little funny things with like the vertical line and the arrow at the side, they're called kets. They're just like vectors. You can think of them just like vectors, how you'd write them like V with an arrow on top of it in linear algebra or multi. And here what we have is we have these coefficients. So one of the other weird things about quantum mechanics in general, actually, so we've already mentioned we have superposition and all these weird things, but quantum states are not exact. They don't give you exact descriptions of exactly what your system's going through. They give you probabilistic descriptions. So when you're doing a quantum computation, you're not saying, okay, do exactly this and do exactly that and give me this exact output. You're saying, okay, let me start you in this general state, this like really random state. And then let me do operations which will push you towards the correct answer of my computation. And what this really revolves around are these numbers. So these are called probability amplitudes. Their squares are called probabilities. Don't worry too much about like the exact math right now, but the point is when you square these numbers, you get the probability that your quantum circuit measures to be in this state. So if you square this, you'll get 1/2. So this says that your quantum circuit will end up half the time in the 0, 0 state and half the time in the 1, 1 state. Okay, so basically what's happening is you took this quantum circuit, you apply these operations, and if you measure the circuit, you run it 1,000,000 times, then 500,000 times approximately, you'll see that your qubits were both in the 0 state, and the other 500,000 or so times, they'll both end up in the 1 state. So that's this like whole probability idea that quantum computation is probabilistic. It's not exact in that sense. And that's really important for a lot of quantum algorithms. That's how they're able to take advantage of getting faster runtimes. So any questions so far to this point? Again, like if you have questions, definitely just raise your hand or interrupt and answer them. So yeah, like here, like I go a bit more over like how these vectors work. So there's like the Dirac notation where you have these like funny things I told you about kets, and it tells you like what state is your first qubit in and what state is your second qubit in. So you read off like 0, 1. And you can also represent it as a vector. So if you've taken like linear algebra or multi or some class like that, you're probably more familiar with this notation. So this is basically the vector representation of a 0 bit, okay, or a 0 qubit. And then this is the vector representation of a 1 bit or a 1 qubit. If you're doing classical computation, every time you look at the state of your classical bits, they'll either be this 1, 0, or they'll be this, the 0, 1. That's it. You'll never have anything else. If you have something else, that means your classical computer is broken or it made an error. Okay, but in general, when you're doing quantum computation, you can have arbitrary linear combinations of these. So I was telling you about superposition. That's literally just a vector linear combination of this 1, 0 and this 0, 1, these two vectors. And so when we're doing quantum computations, we'll be doing arbitrary rotations, as they're called, which is basically saying move the vector around in the sphere. So you can imagine something, I guess I can pull up a picture of this, but it's called the block sphere. This block sphere tells you like what state is your qubit in. And you could basically think of it as every point on the sphere is a different state. So as there are infinitely many points on the sphere, there are infinitely many points that your quantum bits can be in. And these superpositions just tell you what are the coordinates, pretty much. Yeah. So this is called the block sphere. It's really useful for visualizing like single qubits, and you'll see it a lot if you do like more research or more learning about quantum computing. Yeah, so you can, yeah.
There's a note here that says you can generate a state vector from a quantum circuit with measurements. What does that mean?
Yeah, so this is more of like a programming-ish note, which like I just noted. That's why I put it as a note. So what's basically happening when you do a measurement is you're collapsing the state of your quantum system. Okay, so like here you have this like superposition, this combination that you don't know exactly what state it's in, and you're collapsing it into a single state. Okay, so just 0, 0, or just 0, 1, or just 1, 0, or just 1, 1. And so that measurement is not a reversible operation. Okay, you've taken like this complex state and you've just flattened it into a single vector. And so because it's a non-unitary operation, as we call it, non-reversible, it can't be processed as easily using state vectors. You can still represent the final state as a state vector, but Qiskit just doesn't let you. It's just a Qiskit thing. So yeah, when you're using Qiskit, like if I do like qc.measure all right here, and I run it again, it'll say cannot apply instruction with classical bits measure, that sort of thing. It's really just because when you start dealing with classical bits, you can't represent them with a quantum state vector in Qiskit. Qiskit doesn't let you do that. So yeah, that's why there's that note. You'll only have to worry about it if you like make a mistake and come across that error. Otherwise, you don't really need to worry about that. It's just a programming detail. Does that answer? Great. Yeah. Any other questions? And yeah, if there's like anything confusing about the code or like the like notes that we have that I'm not like fully talking about, definitely stop. So yeah, those are
How many, like, what dimension is the state vector in?
Okay.
Zero to the n or?
Right, yeah. So when you're dealing with a quantum state, what's happening is for every single qubit, you're gonna have two states that it can be in, right? A 0 or a 1. So every qubit that or two like basis states, as they're called, basis states. It can be in a superposition of them, but the basis that you're computing in is 0 or 1 at the end of the day. So that means that for every qubit, you have two states that it can be in at the end of a computation. So that's why we say if you have n qubits, you need 2 to the n, you need a vector of size 2 to the n to store its state. So you can already check that with this example. Here I told you a single qubit in the 0 state is represented by this vector with two components. So 2 to the n, or in this case 2 to the 1, because we had 1 qubit, is 2. If you have 2 qubits, then your vector is going to have 4 entries. If you have 4 qubits, it's going to have 16 entries, 2 to the 4, and so on and so forth. So this is why it's really difficult to study quantum computers computationally, because for every qubit that you add, you need twice as much memory. So for example, if you want to simulate a Qiskit circuit that has 16 qubits, you're going to need around like 32 to 64 gigs of memory just to store the state of that one qubit. Okay, and then if you add another qubit, that's going to become 64 or 128 gigs. That's already more than most people in this room probably have a computer for. If you have that many, then great, you can do big quantum circuits, but it's really hard to simulate these things. So that's why we're often limited to just studying smaller systems on classical computers. Yeah.
Can you explain how it's taking up that much memory again?
Yeah, so it's literally just because you need twice as many numbers. Okay, so let's say you want to store let's say you want to store the state of 1 qubit. Okay, you need to store 2 numbers. You need to store this top number in the vector and this bottom number in the vector. So I told you, oops, don't do that, please. Oh, it's not going to let me. Okay, fine. So this top number it's the square root of the probability that it gets measured in the 0 state. Okay, so I told you about how like, where is it? I guess I need to delete this measurement for it to run. Oh, I already applied a measurement. Oh yeah. Yeah, there's some funky things about Jupyter Notebook that you need to be careful about. So if you have issues, let me know. Yeah, so when you want to store like this sort of thing, right? You have 1 qubit and it can be in the 0 or 1 state. So you need to store the probability it's in the 0 state, which is like this number here, and the probability it's in the 1 state, which is this number here. Okay, but when you add another qubit, what happens is you have the probability that your first qubit's in the 0 state, and the probability that your first qubit's in the 0 state, and that your second qubit's in the 0 state. And then you have the probability that your first qubit's in the 0 state, but your second qubit's in the 1 state. And then you have the probability that your first qubit's in the 1 state, and the probability that your second qubit's in the 0 state. And then you have the probability that your first qubit's in the 1 state, and the second qubit's in the 1 state. You get what I mean, right? So like every qubit that you add, you need to store twice as many values in your quantum, in your memory. So if you have 16 qubits and it takes, say, 64 gigs of memory, if you add another qubit, you now need to store the probability that all those other 16 qubits were in whatever states they were in, and that your new qubit's in the 0 state, or that's in the 1 state. So now you have two new, like twice as much memory to store. So that's why it's really hard to like do big circuit simulations, because you just need so much memory. Yeah.
Is the flip gate always that 2x2 matrix of those that same configuration?
Oh, this one right here?
Yeah.
Yeah. So I guess I haven't gotten to that, but I can talk about that now. So I told you like these are the quantum states. This is how you represent them. And again, if you have questions about like this notation, definitely ask. I know it's really confusing. But there's these quantum operations, right? So you take your vector and the question is, okay, I have a vector, let's say it starts in the 0 state. How do I model what happens when I apply a quantum operation? And that's done using matrices. So just like in linear algebra, you take a vector and you multiply a matrix by it, right? Like if you want to like rotate a vector, you can multiply a rotation matrix. If you want to reflect the vector, you can apply a reflection matrix. Just like that, all quantum operations are matrices. Not all of them really, but this is like nuances that we don't need to worry about too much for now. Most quantum operations that you'll be dealing with are represented by matrices. So for example, there's something called the bit flip. So if you're familiar with like a classical NOT gate, what you do is you take a 0 and you turn it to a 1, and you take a 1 and you turn it to a 0. That's all a bit flip is doing. And so in a quantum bit, it does the exact same thing for the most part. Okay, so like if you just have a qubit in the 0 state, it'll flip it to the 1 state. So you take this 0 ket and you turn it into a 1 ket. And the way you can compute that by hand, if you want, is to use this matrix. So this is the matrix for a bit flip. You take this matrix, you multiply your vector by it, your state vector, and then you get the output. So if you don't trust me, you can check right now. You multiply this vector by this matrix, and then you get the 0, 1 vector. And that tells you that your qubit's in the 1 state now. So it does this sort of bit flip if you have like a 0 or a 1. It gets a bit more tricky if your qubit's in a superposition. If your qubit's in a superposition, the more accurate way of saying it is that it flips the probabilities of 0 and 1. So like I can work this out on the board. I'll try and write big enough so everyone can see. If you have a qubit, which is in a state like alpha, beta, okay, so this is your alpha and that's your beta. These are your amplitudes. So if you want to like check like what I mentioned, this would be represented like that. Okay, so the probability of 0 is alpha or alpha squared, and the probability of 1 is beta squared. So you put this in this vector, okay, and then you can multiply it by the bit flip matrix. So you take 0, 1, 1, 0, and you multiply that. And then what you end up getting is beta alpha. Okay, so what does this tell you? This tells you that you flip the probability of being in a 0 and a 1 state. Okay, so you didn't flip it from a 0 to a 1 state, you flipped the probability. In reality, let's say your qubit started in the 0 state, it could still end up in the 0 state at the end of it. Or if it started in the superposition, it could end up in the 0 state, but it could also end up in a 1 state. You don't actually know what state your qubit was in until you measure it. So until you go at the very end and say, okay, what state was my qubit in? What state was my qubit in? And you do that measurement, you won't actually know which one it was in. You just have these probabilities that give you an idea for what it could have been in, with what probability. So yeah, whenever you're doing a quantum computation, like again, if you're doing 16 qubits, don't even try to do this by hand. You're gonna have a vector with 2 to the 16 entries. So that's literally 2 to the 16 like alphas and betas down there in your vector. And your computer is gonna have to store that many numbers. So don't do this by hand. But if you were to do it by hand, it's the same thing. You take a vector, you multiply by a matrix. It's just this time it's a much bigger matrix than this. Yeah.
Why do we restrict ourselves to like 1 and 2? Like, is there a physical restriction?
What do you mean by 1 and 2?
Like, we have 2 basis vectors,
Yeah.
but like, is there no reason we like,
Okay,
I mean,
yeah.
besides the like, antiquated binary?
Right, yeah, so,
But-
yeah, that's a great question. So I sort of lied to you earlier when I said that a quantum system can be in 2 states. In reality, they can be in way more than 2 states. But what you do when you're building a quantum computer is you say, I'm gonna pick 2 states to be my 0 state and my 1 state. And one of the biggest reasons for this is because classical computers also pick 2 states. They pick a 0 and a 1, a low voltage and a high voltage. But if you want, you have way more states than the classical computer does. And really, you have them more robustly. Okay, so what you could do is you could say, okay, I'm gonna have three states. So I'm gonna have a 0, a 1, and a 2. And so now every single quantum state vector has to have an extra component. Let's call this gamma, which is the probability that you measure in a 2 state. And now every vector has an extra component. It tells you the probability you're in the 2 state, right? And so on and so forth. So you can do this, and a lot of people do research these. These are called qubits. So like the thing we were talking about earlier were qubits. This would be what's called a qubit, TR for like 3. In general, you have what are called qubits. So like D is your dimension. So like if you have 2 dimensions, it's B. D is B. If you have 3 dimensions, D is TR. If you have 4 dimensions, does anyone know? I don't. But you have qubits, using the Latin analogy, I guess. Does anyone know actually? I genuinely don't. But yeah, at that point, people just say qubits. So you'll say like a qubit with dimension 4, or a qubit with dimension 3, or a qubit with dimension 51, whatever. Right? So those are qubits. A lot of people do research them. It's just, like most of our knowledge about like computation is in binary systems. So it's like helpful to be able to steal that prior knowledge that we have and use it in like new algorithms using quantum computers. Yeah.
It's a Q quart.
Quit?
Q quart.
Quit?
Quart. QUART is the.
Oh, wow. Okay. I would not have guessed that. Sure. Okay. Q quartz. Okay. That's funny. But yeah, you can have Q quartz if you want. It's just like most of the time we don't. There are fewer people working on like Q quartz than there are qubits. But yeah, good question though. Any other questions? So that's like the basic like mathematics. Like at this point, you know pretty much how to do all of quantum computing. Okay, this is most of it. All you do is you prepare your qubits in a state, that's your state vector, and you apply a quantum operation to it. That's the matrix. The hard part is, what quantum state vectors do I use? What quantum operations do I use? How do I represent them as matrices? How do I do this in a way that gives me high probability results, right? Because I told you these quantum computations are probabilistic. The only way that quantum computing ever works is if the probability that you get the correct answer is close to 1. That's a number called the fidelity. The fidelity tells you what's the probability that you get a result which is close to the correct result. And so all quantum operations are about maximizing fidelity. What you'll often do is you'll start in a system that's like 1/2 and 1/2, like it's an equal probability of being anything. And then you'll push it around, using these quantum operations to get it into the correct state. That's what quantum computation is about.
So what's the fidelity of the 1/2, 1/2 thing? What would be the fidelity there?
Well, it depends on what your reference is, right? Like you're always comparing to something else. Like maybe I wanted to make a 1/2, 1/2 state, in which case my fidelity is 100% because I did it. But let's say I wanted to make a 1/0 state and I made a 0/1 state, then my fidelity is 0 because I made the exact opposite. I wanted 1/0 and I made 0/1, or vice versa.
If it's like 1/√3 and 2/√3, then how would you
There's a
calculate?
complicated formula. If you want to see it, we can look at it. Because someone asked, I have to show you guys what's the general formulas for state. I don't even remember this off the top of my head. This guy. So yeah, if you want to compute that for like 1/√3 and whatever the complement of that is, then go ahead. But yeah, but I'm not going to do that right here on the whiteboard for you. Be my guess if you want to. Yeah, I was gonna, and also if you're scared by this row thing, this is where I lied and tell you that all quantum states can be represented by vectors. That's also not true. In general, you need density matrices, but we're not gonna get into that like for today. For today, like you want to like, get used to the basics, and then once you understand like the state vectors and all of that stuff, then we can start talking about density matrices. Next week, we will talk about density matrices because density matrices are really important for quantum error correction. But for now, don't worry about density matrices. For now, all you need to know is quantum states are represented by vectors and quantum operations are represented by matrices. And all quantum computation is you take a vector and you multiply by a matrix. That's really all there is to it. So the question now is like, how do you actually do this? What quantum operations are available to you? Like your qubits can be in any state that you want, any arbitrary superposition. But there's only so many quantum operations that are valid. So I told you that like quantum operations have to be reversible. They cannot be irreversible. That means that if I do a quantum operation, I know how to revert it. There is some other operation that would revert it. So there is a subclass of matrices called unitary matrices. If you see the word like unitary around, that's what it means. It's just an operation that's a valid quantum transformation. So now, like for the rest of the time, I want to take you through like examples of quantum unitaries, quantum operations that you can do, what they do. And then once you understand these, you're ready to, look at any quantum circuit and say, oh yeah, that's an X gate, it flips a bit. That's a Hadamard gate, it puts in a superposition, that sort of thing. And then at the end, we'll do actual measurements and you'll get to see what like results from a quantum circuit look like. So yeah, again, stop if you have questions about any of these, but the first quantum gate that we're going to look at is the most interesting one of them all. It's called the identity gate or the do nothing gate. It literally does nothing. So if your qubit starts out in the 0 state and you run the identity gate, it ends up in the 0 state. If you flip your qubit so that it starts in the 1 state, so I can apply an X gate so it starts in the 1 state, and I apply the identity gate to it, it does not work because I don't have 2 qubits, I have 1 qubit. It ends up in the 1 state. So the identity gate literally just keeps your qubit in the same state it was in. It may seem like really stupid to talk about this, but when you get to quantum error correction, the identity gate is actually used in many cases for things and computations. So it's good to know that it exists.
What does QC.X do?
QC.X flips it. So I guess I should, that's going to be answered in this next cell, which is the X gate. The X gate is the one I showed you here, which flips the probabilities of 0 and 1. So let's say you started your quantum system again in the 0, 0 state, so everything's a 0. And then here what I did is I took the first qubit, okay, so 0, and I applied an X gate to it. So that means I'm flipping it from a 0 to a 1. I guess I should say this, by default, all qubits in a quantum circuit start out as 0. So before this, qubit 0 is equal to 0, and qubit 1 is equal to 0, okay? So you apply this X gate, and it flips your qubit 0 from 0 to 1. And then here what I've done is I've applied 2 X gates to my second qubit. So qubit 1, what I do, it starts in 0. I apply an X gate, that puts it in 1. And then I apply another X gate. That takes it from 1 to 0. So at the end of the day, when I run this cell, okay, it ends up in the 0 state again. Okay, so that means that X times X equals the identity. So there's like this matrix here, right? You can check that for yourself. If you take that matrix and you do 0, 1, 1, 0 times 0, 1, 1, 0, you should get back the identity matrix, which is represented as that. So if you want, you can go ahead and check that I'm not lying to you. That's probably a good idea to do, but that should happen when you do the multiplication. And so that's why when I apply 2 X gates to a qubit, I end up getting the same state back because I just did nothing to it. Yeah.
So when you start the quantum circuit, when you say that both qubits are in the 0 state, does that mean that the I forgot what it's called, but the constant that describes
Yeah, the probability.
being 0 is 1?
Yes, it's 1. So I can write this out as well. So what happens is you start your quantum circuit, okay, it starts in the 0, 0 state. Okay, so this is like the circuit drawing. And so at this point in time, your quantum state is 0, 0. And we don't write the 1 usually, but you can say yes, with probability 1, it's in 0, 0. And so now what I do is I apply an X gate to my first qubit, okay? And for now, I do nothing to my second qubit. So now what happens is my system, I flip the first qubit, so now it's in a 1. Maybe I'll write that like that. It's in a 1, and the second qubit, I didn't do anything to it. So now it's still in a 0, right? And then I move on, I do an X gate to my second qubit. So now it's in the 1 state. So I didn't do anything to my first qubit. Okay, I just kept it in the same state. I flipped it and I get 1, 1. Okay, so at some point, my quantum state vector was in the 1, 1 state. And if you don't believe me, you can get rid of the last X gate. And when you run it, you see the 1, 1. So why does it not end up in the 1, 1 state? Because I applied one more X gate right here. These 2 X gates, they cancel out. So they cancel out and they equal the identity gate, just like we set up there. And so now what happens is your final state is 1, 0. So you flip the first qubit, but you did X twice to your second qubit. And so the final result on that second qubit is nothing. You did nothing to it. Yeah.
These are like the X's to Pauli, right?
Yeah, so if you're familiar with like Pauli matrices from like quantum mechanics, the X matrix here, as we denoted in quantum computing, is also denoted sigma X in quantum mechanics. Yeah, And that's the same for the Y and Z matrices that we'll encounter a little bit later. Yeah. Any questions? This was our first non-trivial quantum operation. So if you have questions about like the questions about the matrix representation or like that like canceling out thing or any of that, let me know. And we'll see more examples. So if you don't fully understand it just yet, don't worry, there are way more examples that'll help you with that. And yeah, it's like, of course, you have this notebook in front of you. So if you want to like try messing around and sell, do different things to it, feel free to see what you can do. But yeah, you can call this like the quantum bit flip gate, but the formal name is the X gate. Okay, so then moving on to the Y gate, or sorry, Z gate first. So the Z gates, this is where it gets a bit more confusing. So before I told you like, oh yeah, like these numbers in front, you square them and then you get the probability. And so this is where you have to be careful about squaring them. So this alpha and this beta are not the probability. They're like the square root of the probability. So you'll notice here, when I run this quantum circuit, I get -1 times the 1 vector, or -1 ket. And you might ask, but probabilities can't be negative. That doesn't make sense. That's right, because you have to square the number. What this tells you is that your qubit has a 100% probability of being in the 1 state, but it's acquired what's called a quantum phase. Phases are another property that's unique to quantum systems. Okay, there are these numbers that appear that can be complex numbers too, not even just real numbers, they can be complex numbers. And there isn't really a physical, when it like in this sort of situation, there isn't a physical interpretation. The only thing that's physical about quantum mechanics are the final probabilities, like -1 squared is 1. That probability 1 is physical, but that negative in front doesn't really tell you anything here. It's just an artifact of how quantum mechanics is structured and how these systems behave. So I know it's like kind of weird to like start thinking like, oh, there's negative numbers. And then as you'll see in the Y gate, you have an imaginary phase. So I told you that like you square them. That's also not true. So I lied to you twice. You can't square them. You take what's called the complex modulus. So if you haven't taken like a class that deals with complex numbers, I can explain this really quickly. It's not too complicated, but you might want to like work this out by hand to make sure. What you do to get the complex modulus is you take the number, so like I, and you multiply it by its complex conjugate. So that basically just means take all the i's and make them negative I. So here, right, we had our amplitude was I. So let's take its complex modulus. We do, okay, first let me show you the notation. It's denoted like this, so like bars on either side, okay, and then squared. So this number you take by taking I, okay, the imaginary number, and multiplying it by its complex conjugate. This is sometimes denoted with something like a star, like that, an asterisk, okay? And this here is equal to -I, because I told you it's a complex conjugate, you flip all the i's to negative i's. So you get I times -I. And if you multiply this out, then you get 1. And now you get a valid probability. So yeah, if you multiplied I by itself, you would get -1. And by the statement I told you earlier, your probability would be -1, which again is not a valid probability. We want our probabilities to be numbers between 0 and 1 that add up to 1. So here we now have a valid probability. Yeah.
Adding a negative doesn't change the probability by 2. What is the use of?
Right. So quantum phases are still interesting. So in this case, it didn't do anything. Okay, because what happens is when you square it, you just get the number back. And there's no other numbers for it to be compared to, right? Like it's 100% probability. The time it's interesting is when you're doing a computation where you want to store some of your information in the phase itself. Okay, so in general, like these alpha and betas can be represented in this following form. Alpha is equal to R, okay, so like a real number R times a complex phase. So if you haven't seen this thing, don't worry about it too much, but it's basically just an arbitrary quantum complex number, okay? This is just some complex number. Sometimes what you'll want to do is store your information in not just the R, the real part, but also the theta, okay? So that is an angle, and you can do a lot of interesting stuff using these phases. So if you've heard of like quantum phase estimation, which is which can be used as part of algorithms like Shor's algorithm, it relies on these quantum phases to exist. Shor's algorithm would not work if you couldn't have these complex phases. There might be another way to make it work, but the way it's formulated would not be the same without these quantum phases. So it's a very central fact of quantum mechanics. And yeah, I know it's really hard to get used to the fact that like they're there, you have complex numbers and negative numbers like running about, but they're really important to how we do computation. And you'll start to appreciate them more as you do, more interesting examples than this. Yeah, any other questions about things so far? Yeah, we're at 6:50, so I'm gonna like move on a little bit more. So we have two more big operations. This isn't the list of all quantum operations, by the way. This is just like a subset that you'll find like really often. The next gate, so this is where it starts to get even weirder, is you have the H gate, the Hadamard gate. This is the superposition gate because it takes a qubit, which is in the 0 state, and puts it in an equal superposition of 0 and 1. So if you're curious about the matrix representation, the matrix representation is H is represented by 1, 1, 1 minus 1, 1 over square root of 2. So this is the matrix for the Hadamard gate. And when you multiply it, for example, by a 0 ket, okay, so a qubit in the 0 state, you get an equal superposition. So 1 over square root of 2 of 0 plus 1 over square root of 2 of 1. Okay, and as I said before, the probabilities are the complex moduli of these numbers. So you take this number and multiply it by its complex conjugate, which is just itself, and you get 1/2. And you take this and you multiply it by its complex conjugate, and you get 1/2. So this tells you you have a state which is 1/2 0 and 1/2 1. What that means is when you go, okay, you implement this quantum algorithm on your quantum computer, whatever quantum computer modality you use, and you do 100 measurements, okay? You run it 100 times, and you'll generate like a bar plot, okay, like a histogram, whatever. You say like 0 and 1, and then like the frequency, let's say like how often do you measure them? It'll be like, maybe like 49% 0 and 51% 1. It's not always going to be exact. If you have a perfect quantum computer with no noise, no error, which physically cannot exist, then you'll get 50-50. But in general, like in reality, you'll get like some numbers near 50-50. And your fidelity is telling you how close to that are you really. Yeah.
I was gonna say, aren't you still hurt by sample size?
Can you say that again?
Aren't you still hurt by sample size even if you have a?
Right, yeah. So for example, okay, let's say you do one measurement. You only run your quantum circuit once and you measure it once. How many data points can you get? 1, because you only did one measurement. So your bar plot is going to look like this. It's going to look like 100% 1 and 0% 0, right? Because you only did one measurement. Maybe it'll be like the other way around. Maybe you'll only get a 0 or only get a 1. So you need to do this measurement many times. You have to collect many samples. This is what's difficult about quantum computing. You can't just run an algorithm once and be done, like you do with a classical algorithm. You have to run it many times and collect these data and these statistics and benchmark it. Yeah.
Why is a perfect quantum computer not possible?
Sorry, say that again?
Why is a perfect quantum computer not possible?
Yeah, so what happens is when you're dealing with quantum mechanics, there are fundamental limits on how precise you can be about certain measurements. So if you've heard of Heisenberg's uncertainty principle, okay, this tells you that you cannot know where your qubit is and how fast it's moving pretty much to infinite precision. There is a hard limit that you can never do better than in like the total uncertainty, let's say. I don't want to like worry too much about like the exact way it works, but the point is you can't know everything about your system to perfect accuracy. And because of that, you're always going to have these little errors that occur. The goal with quantum computing, especially quantum error correction, is to minimize them, have less and less of that uncertainty, and get more and more confident results. If you do 1 trillion measurements of one quantum circuit, then you're going to do pretty good. Like you'll have a pretty good chance of getting the right data out. But if you only do like 2 or 3, you won't. So there's this question of like how many times you have to do it. That's something that we're actually trying to answer for our project. How many times do we need to run these quantum circuits to get good data about them? Great questions, yeah.
So I know you said that the output of the 0
Yeah.
qubit is gonna be 1 with equal probabilities, right?
Yes.
So I tried flipping it on a 1, and instead it gave me like 1 being positive, 1 being negative. Like, why does that happen?
Okay, so what state did you prepare it? So you have your quantum circuit, let's try this out. You have your quantum circuit, okay? You have 1 qubit?
Yeah.
Okay, you have 1 qubit and it starts in 0 state, so by default, what operations did you do to it?
The X.
Okay, so you applied an X gate. Okay, so before you had it in the zero state. So if you measure this guy, you're always gonna get zero, right? Because this is 1 times 0 and 1 squared is 1. Now you flipped it. So now you did x times 0. And as I was like saying before, x times 0 is equal to 1. So you end up with the 1 state. And its amplitude is 1, right? That's just how the matrix multiplication works out. And so at the end of the day, you have a qubit, which is in the 1 state with probability 1. So you're always going to measure it in the 1 state. Well, okay, up to noise. So that's always like the catch, you know, like 99.99% of the time you should get 1. And what did you get instead?
I was wondering, after that, I applied the Hadamard gate.
Oh, right, sure, yeah. Yeah, you put a Hadamard gate, yeah, and then?
And then I was just wondering why the,
Oh, right, yes, so what I told you somewhere when I drew it, yes, so this. When you apply Hadamard gate to a 0, you get 0 plus 1, sorry, now I understand your question. But the Hadamard gate operates differently on different qubits, okay? So if you apply the Hadamard gate to the 1 qubit, so a qubit in the 1 state, you get 1 over square root of 2, and I'll like just factor out the square root of 2 because it's in both, you get a minus sign. So this is one of those quantum phases we were talking about. If you actually do a measurement, you're still gonna get 50-50. There just happens to be this phase which comes in between. So I'm guessing you saw that minus sign? Yeah, that's exactly it. Because the Hadamard gate applies different operation, or it works differently for 0 and 1 qubits.
Okay, so it seems like the gates are all entropy preserving except for the case of the Hadamard gate.
Sure,
Kind of
sure.
confusing me.
Yeah,
Like, normally That's always
Uh-huh.
as close to certainty
Yeah,
for a certain output, except for this one. So how does that not violate the determinism part?
right, so I should say this, it's not determinism in the sense that you always know what's always gonna happen, like for certainty, like for sure. There is still probability involved. But you can say it's sort of deterministic in the sense that when you apply a Hadamard gate, okay, you know how to reverse the Hadamard gate. Maybe deterministic isn't the best word for that. I should really just say reversible. There are different fields of physics will define like deterministic in different ways, depending on what you consider like possible. But yeah, maybe if you like it more, then like the more like statistical word would be reversible and not deterministic.
Okay, I was sorry to take up time. I get.
Yeah, no,
I'll
worries,
come
no,
back
it's
after.
a good question. It's a good question. I should have worded that better.
When it comes back to you.
Yeah. Any other questions? I know it's almost 7. I guess we'll continue for people who can stay, but if not, then we'll have the recording afterwards. So if you need to go, feel free to and just watch the recording back. Yeah, any questions before I move on to the last one, which will be our first encounter of a 2-qubit gate. So this is the C0 gate. So the C0 gate is a little bit trickier to describe because it's what's called a conditional operation. So that means it doesn't always work the same way. It depends on other qubits. So for example, let's say you have a quantum circuit, okay, and it's in the states 0 and 0, okay? You can do a C0 gate, sorry, which is like a dot here and a little like X in a circle here. This is called the control, and this is called the target, okay? What this basically is saying is this. If my control is in the 0 state, I'm not gonna do anything. If my control is in the 1 state, I will flip the second qubit, okay? So here, your first qubit's in the 0 state, that's your control. So at the end of the day, you're gonna end up with 0 and 0, right? It was in the 0 state, you're not gonna do anything. Well, let's say your qubit started in the 1 state, okay? Your control starts in the 1 state. Then it says, okay, my control is in the 1 state. So I'm gonna go to my second qubit, and I'm gonna apply an X gate to it, okay? So it applies an X gate. And now what happens is you end up in the state 1, 1. So that's why when you run this circuit that I've constructed here, this is like really cool. This is quantum entanglement at its like in action. What you do is you take your quantum system and you put it in superposition of 0 and 1. So it has equal probability of being in 0 and 1 in your first qubit, okay? So this is a 0 or a 1. So now you can sort of imagine like, to go with the weird like multiverses hypothesis, you can imagine there's a universe where your first qubit is a 0. In that universe, it doesn't do anything to your second qubit, right? Because the control says, okay, it's a 0, so I'm not gonna do anything. In another universe, your qubit ends up being a 1. In that universe, because your qubit was a 1, the control looks at it and says, okay, I'm gonna apply an X gate, and it flips your second qubit. And so what happens is you have 2 universes that occur, okay? So this is like universe 1 and you have universe two, I guess, let me draw it over here. You have universe two where your qubit starts out in the 0 state. So the Hadamard doesn't flip it to a 1, it keeps it as a 0. And then you apply the C naught gate, okay, and nothing happens. You end up with a 0 and a 0. So these are equally likely. The Hadamard puts you into an equal superposition of these two initial states for the first qubit, 0 and 1, right? 1/2 and 1/2. So in half the universes, you're gonna get 1, 1. In the other half, you're gonna get 0, 0. Also, I hate the universes argument for whatever. So I'm just using it for like, visualization in your head. And so what you can say at the end of the day is half the time you're going to end up in the 0, 0 state, and the other half you're going to end up in the 1, 1 state. Okay? And the reason why this is entanglement is because let's say I have qubit 1 and you have qubit 2. Okay, so like you store it in your own quantum computer and I have qubit 1 in my own quantum computer. If I apply a C naught between my qubit and yours, with a Hadamard in front, then and then I measure my qubit. Let's say I measure my qubit and it's in the 0 state. Okay, then I know automatically that your qubit is in the 0 state. I don't have to ask you any questions. Nothing has to be done. No, I don't have to talk to you. You don't have to talk to me. No information transported. I measure a 0 and I know you're in 0 immediately. If I measure a 1, I know you're in a 1 immediately because my state vector says you're either in 0, 0 or 1, 1. If I'm in 0, you are in 0. There is a 0 probability that you are in the 1 state if I'm in 0. And this is what like Einstein really hated, like 70, 80 years ago when he was like learning about quantum mechanics and all these discoveries people have made. He didn't like this because it seems to violate like locality. Like if I'm doing something myself and you're doing something yourself, how are we able to like exchange this information instantaneously? Like almost like faster than the speed of light, right? And that's what like Einstein hated about quantum mechanics, but people have proven that this is possible. They've generated these states called Bell pairs. That's the name for this and then a couple other states. They've generated these Bell pairs experimentally across the world, and they've shown that they're able to get these measurements that can't be explained in any other way. Yeah.
So have we like in that time like figured out if it's just like a knowledge update or if it's actually causing the other qubit to actually become a 1?
Great question. Yeah. So what Einstein and then Podolsky and Rosen proposed is that there is actually a hidden like factor. There's a hidden factor called the local hidden variable, okay? So there's this some like mysterious state, like underlying you and me. We don't even know about it maybe, but there's this some like underlying like channel that just set up our qubits to happen to be in this entangled state. So we didn't communicate. It just they happen to be in this like special prepared state by some third party, this like really like it's called the local hidden variable theory. And what these experiments did, okay, these Bell pair experiments did, is they proved that mathematically their results cannot be explained at all by this sort of theory. As in, it's not even just like, oh yeah, our data is really good. It's our data if our data is correct and this theory is correct, they are mathematically contradictory. So that it's a very, very strong argument. Like I cannot understate how strong of an argument they made in proving that this is real.
Yeah, kinetics.
People have like all these crazy theories like multiverses and all that stuff, but yeah, we don't fully understand like why exactly this stuff happens. But we're here and we use it for computations. So yeah. But yeah, so like one more thing about quantum operations before we move on to like the last step, measurements, is that quantum operations don't commute. So this means if I apply an H gate and an X gate versus an X gate and then an H gate, they're not going to do the same thing. Okay, the result will not be the same. And if you doubt that, then go ahead and check for yourself. You'll see that when you run these, you either get like minus, or here I did X and Z, but you can do X and H, whatever. And you'll get like different results, these different measurements. So yeah, that's just something important to know. And then lastly, there's measurements. So, I talked about like all these operations you can do it, algorithms you can construct. At the end of the day, you have to do a measurement and you have to say, what did my system tell me? That's what these guys are for. These are like little like meters. And they basically say, take the state that's in this qubit, measure it, and put it in my classical bit. Okay, so now it's in classical bit, it has to be 0 or 1. It can't be a superposition anymore. This is this like whole like wave function collapse thing you may have heard of. We're taking this arbitrary superposition probabilities and collapsing it to either 0 or 1. Okay, and we can do this for each of our qubits. And when we do it, we can do measurement results. We can get a lot of measurement results. So this is actual data from a simulation that says, if you run my quantum circuit like 1,000 times, these are the measurements I got. One time I got 1, 1, another time I got 1, 1, and then I got 1, 0, and then 0, 1, 1, 0, so on and so forth. And then you accumulate these statistics about your data, right? Like how many times I get 1, 0, how many times I get 1, 1, all that. And then you can put in this histogram, just like I drew before. And you can see it's like an equal superposition, sort of across like all these 4 states. So yeah, that's really all there is to it. You made your qubits, you paired them, you did quantum operations, you measured them, and now you're done. Except your measurements suck and you have all these errors, and that's why you need to use quantum error correction. That's why you need to come to next week's workshop to learn about quantum error correction. Yeah, question.
Sorry to ask a question.
Yeah, yeah.
Everyone wants to leave. I mean, not that everyone wants to leave, but people are hungry. So when you're doing a measurement, do you have to specify like what basis? you're
Yeah,
measuring?
so I told you about this whole like block sphere thing, right? What a measurement is really doing is it's saying, okay, I have this like arbitrary vector, right? Like it's somewhere in my sphere. How much of it is along one axis? That's your measurement basis. So if you say like, okay, I want to do a measurement along the z, I'm saying how much z is in my vector? Like to put it like in really layperson terms, how much z is in my vector? The real mathematical term, if you've taken like linear algebra, is what's the projection of my quantum state onto the z basis. And that's what these like measurements are really telling you. It's telling you when I project your qubit onto a z basis, I get a 1 in the z axis or a 0 in the z axis. Different probabilities, and those are plotted here. Yeah, that's it for the workshop. Sorry, we went like 5 minutes over time. If we started earlier, we'd have been fine. But yeah, we'll be sticking around if you guys have questions. And if not, this recording will be on the Discord, and then this notebook is also linked on the Discord. So if you need to access stuff like later, feel free to. If you have questions about like stuff you've ran or anything I talked about, go ahead and ask them in the Discord. Don't like be afraid at all. Even if it's like a silly question, like what are qubits again? Don't worry at all. Just go ahead and ask them. And yeah, we also have this resource flow chart, which is supposed to be like, like along with these workshops, if you follow this resource flow chart, you'll get like a more deeper understanding of everything I talked about. But yeah, that's it for the quantum computing workshop. Thanks everyone for coming and sticking around. Next week, same place, I think, is next week here, but we'll announce the location of next week's meeting in the Discord, but we'll be meeting same time next Thursday for the QEC workshop, where we'll show you guys about quantum error correction and how that all works and how you get better measurements results than this. That's the real question. Yeah, thanks for coming. Oh yeah, there's also a meeting tomorrow if you guys have any questions, 2 to 4 in Howey S204. The information will be sent on Discord like later tonight or tomorrow morning. If you have questions, you know, stop by tomorrow between 2 and 4. Feel free to, we'll be there to answer any questions you have. Yeah. Thanks for, oh yeah, next week we'll be in Bunger Henry, so it's that other building. So yeah. Yeah, thanks guys for coming. See ya.
Or-